I will present you the situation of a French project including the 3 companies involved in the breeding scheme of the Lacon and Manèche breed, the Richer breed in France, and INRA and Institut de l'Élevage to check if is it possible to move from the classical breeding scheme that are managed today to a genomic selection scheme in more or less in the near future. So as I said, 3 companies are involved in this project, 2 in Lacon breed, 1 in Manèche breeds. They are the company in charge of the breeding scheme of this in these breeds with extensive use of artificial insemination, around 500,000 AI in Lacon breed each year, and about 120,000 AI in Manèche breeds. We have at the moment two research projects in progress with this company between INRA and Institut de l'Élevage to build reference populations in these 2 breeds. And the main goal are to produce technical and economical parameters of possible genomic selection schemes for these breeds to permit this company to decide probably in 2-3 years to move or not to a genetic selection scheme. So to show you the situation, the present situation, at the end of the last year, the available reference population based on the genotyping of AI rams was, as shown in these figures, around 2,800 AI rams compose a reference population for Lacon breed, and close to 1,300 for the Manèche red-faced breeds. As you can see on the slide, since the rams born in 2003 in the Lacon breeds, around all the rams of given birth years are genotyped, and in Lacon breed it's around 400 rams per year. And for the Manèche red-faced breed, quite all the AR rams of birth years are genotyped since 2000, and it represents around 120 rams each year. So all these rams have been genotyped using Illumina Ovine 50 B chip. After editing about 75% of the SNP of the SNP are used for GEBV computation, and you have the classical causes of elimination presented in this slide. So some time to explain what we do when we carry out a genomic evaluation test based on the interval recommendations. The idea is to observe the evolution of a given group of rams of their EBV over time. And the first time, it's what is called by interval test reduced data set. It's the time where the rams is selected to be progeny tested. So at that time, he has no daughters, and for dairy sheep, it's 6-8 months old ram chosen to enter the AI center to be progeny tested. So, the idea is to look to have a first UBV estimation at that moment, and when the daughter, the progeny of will be recorded n years later, you have a second situation which is called by interval full data set. And it's in Deriship, it's 2-3 years later, the first crop of a daughter after progeny testing, which allowed to compute UBV based not on parentage information as it was the situation in the first term, but on the daughter, the progeny of the progeny test. So, it's the first idea. The second is that we have two kind of size of RAMs when using GUBV approach. The RAM are split in two groups, the reference RAM and the validation RAMs. The reference RAMs are the older, where you have always pedigree, SNP, and phenotype, which are daughter yield deviation information. And this older RAMs are used at the first situation with a reduced data set to predict the relationship between SNP and phenotype, daughter yield deviation, to use this prediction to the second group of RAM, which are the validation RAMs, the young RAMs to be progeny tested, which at that time have no daughters. So these young RAMs at that time have only pedigree information and SNP genotypes. So either they can be select classically using only parentage information without genomic approach, or with GUBV, the GUBV can be computed knowing the relationship between SNPs and daughter yield deviation of the reference RAM to be applied to predict the UBV, knowing only the SNP genotype. I speak about validation RAMs. We have not yet the daughter at that moment. And so now we are looking only at the validation RAMs in this second slide. Always at the two time reduced data set and full data set. At the reduced data set, when you are using BLUP because conventional GBV, at the reduced data set, we have BLUP for this one, BLUP with a subscript R to say it's a reduced data set. And EDC, which is effective daughter contribution, more or less, which is the number of daughter for the given RAM. EDC subscript ERR also. And you have, if a genomic approach, the GUBV, which, and if I am using JBLUP, I will call it JBLUP R for this young RAMs. For validation RAMs, which is based only on SNPs without any daughter to be included in this GBV. And 2-3 years later, when the daughter arrives, and we are in the situation with full data set, we have either in for conventional UBV, BLUP, and the daughter yield deviation for these animals, which are the actual phenotypes of these validation RAMs. And of course, GBLUP, including SNPs, genotypes, and daughter information of the RAMs, which, corresponding to daughter yield deviation. And what is computed as criteria to compare conventional UBV and genomic UBV are different criteria. Of course, correlation between phenotype to predict in full data set total yield deviation and BLUP or JBLUP at R situation of subscript BLUP and JBLUP when the young rams have no daughters. The second computation is the regression model of the total yield deviation of the BLUP or JBLUP predicted without any daughters. What is expected, of course, is that what I written R2 is higher than R1 for correlation between total yield deviation and BLUP or JBLUP with a subscribed R. And for regression model, we expect that R square of the model 2 is higher than R square of the model 1. And if all is running well, B1 and B2 are 1. If, and it's very important, if the sample of validation RAMs is representative of all the RAMs of the birth years, and it is very sensitive, if at only 10% of the young rams are not genotyped, and for instance, is the worst, rapidly, dramatically, the regression B1, B2 will be really only about 0.6, 0.7, very lower than 1. So, to respect speech time, I will present a result only of the correlation R1, R2, one group of criteria. I have no time to present all the results because I want to explain the idea where we are and when we expect to do, and it can be done using only the result of the first criteria R1, R2. So we, for now about a year, we have carried out several genomic evaluation tests, and the first one was available in Lacon. It is called Test 1 in last summer, and we were so happy to start the computation that we made a mistake. As you can see, we use the same data for the reduced and full data to 2010. It is false. So we include too many information in the reduced data at the first test, which will have two consequences. We will overestimated the efficiency both for classical and genomic approach, and we will overestimate more the situation for classical than genomic approach, and it will reduce the gap what we expect between classical and genomic approach because of these faults. But I have mentioned this result because a lot of other tests done within this first one are relevant regarding the conclusion when we look only at the GUBV results. So it's the reason why I maintain this test, but it is not correct regarding interval rules. So the correct one is the second for Lacon, the test 2, where we don't make the mistakes to use the same amount of data for reduced and full data set. So the reduced data set was the situation in 2007 versus 2011 for the full data sets. And the total number of reference RAM, the learning RAM, was 4,000 in Lacon, of which 1,000 close 600 are genotyped. And the validation RAM was the two younger birth years of RAMs born in 2007 and 2008, and which 681 Lacon RAMs. The same test, I will show you a result regarding the same text for the managed red face breed, including about 1,200 rams for the reference population, and close to 300 rams for the validation population, which is also the two last cohorts of AR rams born in 2007 and 2008. So some results now. The first test carried out in Lacan breed, you have always a gain in a genomic situation compared to a classical blob situation. And for instance, the correlation increase from of about 15% for meal kill. And you have the situation when you compute clearly, you carried out carefully the test, which is a test 2. You can see, for instance, that both the correlation decrease because we include only the two data need at the reduced situation. Reduced data situation for the two correlation reduced for blob and J-blob, but they reduce more for blob than J-blob, and the difference, the efficiency is higher when we compute carefully the test, because it moved for 15, 10 more to 20 more. The second result that I want to show you is when looking only at the genomic GUBV result, whatever the method used in Lacan breed, J-blob, Bayesian CP, PLS, or square PLS, more or less the results are exactly the same. So you have not a method which provide you really clearly best result. And what is clear that is that J-blob is the more rapidly computed method and more clearly used. And it is not relevant to decide to implement, for instance, a Bayesian method, which is very time-consuming and it don't increase the results. On the other hand, for the J-blob method, what is important, it is not the method, but the genetic structure of the reference population. You have the basic result with all the reference population where the correlation is 0.45 for meal kill for the Lacan breed. And if you remove from the reference population the non-genotyped rams, you decrease a bit the efficiency, but not very on a large scale, only about 10%. It's the same if you remove the older rams born before 200,003. But if you have the bad idea to remove the fathers and grandfathers of the validation population of the young ram, you dramatically decrease the efficiency by a third. So it's clear that what is important is that the closely related parents of the young ram you want to estimate are included in the reference population. So now you have the result to compare in the same situation, test 2 and test 3, the Lacan and Manesh red face results, and the good joke for the good result, and at the moment the Manesh breeders are very happy. It is running more efficiently in our test at the moment in Manesh breed than in the Lacan breed. It's a bit more efficient, despite the reference population is smaller. And what can explain such results? Some comparison now between French dairy sheep and dairy cattle. What are the main factors to explain the GUBV efficiency? Of course, the size of the reference population. And if we look at this first factor, it's the Montbéliard or Lacan and Manèche breeds are more or less comparable, of course, smaller than the Holstein breed, and they are only French reference population for Holstein breed. They are using a bigger one now with Eurogenomic. The second factor of explanation is the number of daughters in the progeny. It's around 30, 40 in dairy sheep, 80 in dairy cattle. And the main point is the number of daughters for the reference size, which are the accurate information for the learning process. And of course, it's very disadvantageous for dairy sheep compared to dairy cattle because there are 1,000 daughters per learning bulls in cattle versus around 100 daughters for learning rams in sheep. So it can't be so efficient. And maybe the main point is the last one. In fact, the genetic variability of the dairy sheep breeds is very higher compared to dairy cattle breeds. You can, for instance, explain it as effective size of the population, which is around 50 for Holstein breed, and compared to 250 in Lacan breeds. So you can expect to be so efficient to predict because the genetic variability is really higher in dairy sheep compared to dairy cattle. And when we put together the same criteria to compare French dairy sheep and dairy cattle situation, you can see you know now that the relative gain moving from blob to J blob in Manèche or Lacan breeds is between 20 to 40%. 40% is not too far away from the Montbéliard result, which is 57% for the same criteria. Of course, it's clearly smaller than in Holstein breed, which is 82%. And it is probably clearly in relationship with the fact that the effective size of the populations are very small in dairy cattle compared to dairy sheep. So, for the project, the dairy sheep company in France, we assume that the reliability of the GUBV will be, in fact, between the parent average situation and the reliability of progeny tested rams. I mean that the reliability of GUBV will be around 0.4.7, which is clearly smaller than around 0.6, 0.7 for progeny tested rams, and of course best than parentage average situation, which is only 0.3. So what is the situation in terms of genetic gain per year? We assume that the reliability will be smaller for genomic breeding scheme compared to conventional one. And the limitation of general interval will be limited in dairy sheep compared to dairy cattle. So the main key will be, in fact, genomic selection pressure. Clearly, how many young rams will be genotyped to select the best one to as elite rams at 3 months old. So there will be a balance between breeding and genotyping sufficient candidate young rams to select to have probably high enough genomic selection pressure at 3 months old, and for this point we will increase the cost compared to a classical breeding scheme. On the other hand, we expect to reduce probably by a third the total number of live AR rams which are needed because we are using fresh semen, and we expect to reduce cost of the management of the livestock of AR rams. But will the balance be at least equal to expect to have the same genetic gain as the classical breeding scheme with the same cost? At least to to expect that the company will move to genomic selection programs. So to conclude, at the moment, what is our situation? We have available reference population in French Lacan and managed derivative breed. No problem at this point. The first task has been clearly achieved. It is obvious that the genetic structure of the reference population, I mean, it is that the father, grandfather of the candidate worms have to be in the reference population. It means that you have always to update the reference population years after years. Clearly, it's more important than the method used to compute GUBV. It is also in favor of the fact that probably we have no major gene in the trait included in our UBV.
1 minute.
We assume that accuracy of GUBV will be, of course, higher than accuracy of parent average situation, but will be lower than the accuracy of a provenance. And clearly, it is we have to accept it, and probably because we have a clearly low linkage disequilibrium in dairy sheep compared to dairy cattle, at least three times smaller. And what we are doing now, we have a different way to try to improve our GUBV computation. First, we have a problem of overestimation of unirams, which was described yesterday by the New Zealand speakers in dairy cattle. We have the same problem that we have to face. We have compute one-step versus two-step approach, and the results are interesting on this point. We discover problem of calibration between conventional and genotype data that we have not yet solved at the moment. And of course, we will have also a multi-breed approach, Lacan and manage, to see if it is interesting or not. But particularly between manage and Lacha, given the fact that in the manage and Lacha breed, we have in fact 4 lines, and we have a project with Lacha genotyping too. And because we don't forget that our final goal is to permit the French breeding company to decide, probably in 2-3 years, to maintain the classical breeding scheme or to move to genomic selection breeding scheme.
Thank you.